All right. Well, I think this is a nice segue from this morning's, the first presentation, and we're getting a little bit of a range of things. This is about innovation. What I'm going to present is really a true innovation also for the work that I traditionally do. The background is on structural and civil engineering, focused on a lot of material science. And I think when we get out of our comfort zone, that's when we learn most. So I'm certainly getting very comfortable here. So the presentation is on scalable carbon removal solutions for the cement industry using algae. So, show of hands, how many of you have heard algae and cement in the same sentence before? I'm glad, so I'm not alone. I'd say that's about 20% of the room. And hopefully by the end of the presentation, you can all put your hands up. We'll see that the presentation offered earlier before by Will is looking at a specific area of the carbon, reaching carbon neutrality on the material aspect of things. Does anybody know how else we're going to reach carbon neutrality in the concrete and the cement industry by tackling what areas? Shout it out if you know.
Productivity.
All right, productivity, I love that, yeah, we can certainly reduce that. What else?
Challenging design modes.
Yeah, I mean, AC7, not this conference, but maybe the next one, yes. Transportation, right? We talked about in a previous conversation, right? Lighter weight materials, you can put more stuff, less transportation. This is usually a big factor. What else?
Recycling.
Recycling, yeah, right? Don't throw it away. And a good point with the war going in Ukraine, they say, how are we going to rebuild that city? How are we going to throw away all the rubble from those buildings? And there are solutions of looking at reusing that rubble, actually using it with non-metallic, non-reinforcement, which is, doesn't care about the corrosion. So yeah, very, very important. We've got to reuse what we have. And we're in the decade to make it happen. Has anybody heard that expression before? And the decade is already 3 years into it, and we're not really making it happen. We are relying, in order to reach a net zero industry, we are relying on technologies that do not exist today. They don't exist. And we were just looking at savings in clinker production. That's about 11% of the whole bunch of things that we have to reduce. More than a third is this CCUS. How many have heard of carbon capture and utilization storage solutions? A lot of them is like throw it inside the soil, right? Sequester it. And concrete that miraculously absorbs CO2, like the magnesium material that you mentioned before, and can sequester CO2, right? So a lot of that's what that third is referring to. We have decarbonization of electricity. So all the Teslas in the room, although you need, I think, about 100,000 miles before it actually starts to reach its carbon neutrality, but that's a different conversation. Zinc or recarbonization, another 6%. Savings in cement and binders, material related. So a big portion of getting to net zero is this magic term of carbon capture, utilization, and storage solutions. And I'm going to focus on that. I'm going to offer one innovative solution that we're working on at the University of Miami in partnership with carbon biocapture. But the concept is very simple, right? Something emits CO2, and rather than let it go into the atmosphere, just capture it, hold it somewhere, store it, throw it into the rock pores, put it into existing building that can absorb through the materials, or capture it with algae, as we will see. And the bottom line on this is best and most efficient if you do it from the point source, right? Whatever is a emitter, and this is the images of all these cement plants and other plants that we have, that's really where you get the bigger buck for your investment. But it's not the only place, right? In 2009, the National Academy of Science, Engineering, and Medicine established this research agenda on, NETs, negative emission technologies, which is not only at the point source, but it could be just from the air, right? The cities with smog, with a lot of pollution, you can capture the CO2 on that air and also store it through removal carbon dioxide possibilities. So the innovation that I'm talking about today is microalgae photobioreactors. So from the 20% individuals in the room that heard algae and cement in the same phrase? How many of those have heard about sort of algae being used in this way to capture CO2? So that's about maybe a third of the 20%. So these are actual photobioreactors, right? Algae needs light to exist, and that's the photo part of it, and it reacts with light and whatever you insert into these panels. And needless to say that microalgae, or these algae, are microorganisms that carry out the oxygen photosynthesis, basically a chemical reaction that uses energy using water as an electron donor to release oxygen as a byproduct. In other words, it's eating the CO2 in order to live. That's how we capture those emissions. And the byproduct, sometimes called the biomass, which we will see is a buy-off product of the process of the microalgae. And I have a time scale there, thousands and thousands. So algae have been around since the creation of Earth. So these are very well evolved and developed materials, right? They've gone through billions and billions of years. And hopefully, we can rely on that nature to allow that process. So how do they work? And again, very simple without getting into proprietary technology. But you have a point source emission that, by the way, is not only CO2, right? We might have nitrate oxides, sulfur oxides, depending on the type of industrial emission. So if we look at a steel mill, any industrial process that releases any type of green gas house emission, those can be captured and avoided to be removed. So it's not only CO2. That gas is injected into the panels, which we'll see soon. The algae that live within the panels will eat and absorb those emissions as part of the process. And then a biomass is provided as a byproduct. And depending on the type of emissions that you have, the biomass can be used in very different ways. One way that I love, how many beer drinkers in the room? Please raise your hand. Oh, okay. So beer is basically CO2 production, right? Nobody talks about stopping beer production to solve climate change, by the way. I should say that. But so if you were to capture the CO2 from a beer production using this technology, because those are clean gases, right? There's no heavy oxides, no heavy metals. One of the byproducts is used, for instance, for spirulina, which is sort of a beauty product that makes you look better, healthier, smarter, and all the other things. Not sure about that, but you wouldn't be able to use spirulina from a cement plant production. But a big one is biodiesel and biofertilizers. That's what a lot of algae solutions claim is there, but in order to do that, it's all about scale and quantity. You need to produce biomass in humongous amounts, right? Biomass, by the way, 90% of it is water. So you have to extract it, and then you're left with, the golden part. But there is potential. Is see a little video demonstrating that from the flume stack of a cement plant, you can put a bypass to those gases, and then depending on the availability of space, restack them and feed them directly into a series of these panels. Remember how I said about scalability? So we're only looking now at a single panel. Those are the micro bubbles that are ejected from the bottom. And a lot of the technology is having the gas being dispersed into smaller bubbles in order for the algae to be able to eat away the CO2. And what you're looking at, that would be a projection of a farm, right? Eventually, this is a photobioreactor farm. You probably need about 12,000 of these panels, each panel being about my size. We'll see a couple of pictures. But it is a scalability is an issue, right? So having a modular approach, which we will see, is very critical. But you're looking at space is one of the main restrictions right now, where you need to be able to fit them into the physical landmass that the point source will have. So what is innovation? The innovation is, number one, in terms of algae, not using genetically modified algae. This is a huge issue, because many algae, in a sense, are trained to do something, but they're foreign to the environment. It can create contamination of biodiversity and many other things. It uses a selection of natural, local, available strains. So we developed some for the University of Miami, which we got over from our Osceola Lake. It's a lake that we have on campus. We extracted some from them, and we selected those strains. And then those strains are adapted in order to maximize the capture of depending of the emissions. If it's CO2, sulfur oxide, nitrate oxide, from the flue gases, in this case of a cement plant. And the system can also be used to capture atmospheric gases. So we're looking at developing a fenestration system of the panels to place on buildings and then extract the output from the buildings and insert them into the same system. So even though I'm focusing on cement, there's a versatility of the product that it has. And this is not theory, even though the videos I've shown so far appear to be. There have been 2 plants, the first one in Chile from a coal-fired thermoelectric plant in Ventanas that has been working for 10 years, actually 12. So over a decade working nonstop permanently, capturing at about higher than 80% efficiency. The gases, and this is how the plant looks, is about 35 total panels. And you can see the panels are in real size. The input of the blue lines, those are the water that is used as it evaporates or whatnot. And in the bottom of the panels, you feed the flume gases. Also, for the last 5 years in Colombia, in Cartagena, a cement plant from Argos has been operating, capturing the direct emissions using the same technology. And I think we're looking at an 85% capture of the CO2, 100% of the nitrates, and 95 of the sulfate oxides. With different strains, again, adapted locally for each of the regions. And I should say that why these regions? Chile is much further south from the equator. Huge different changes. So as you look at a calendar year, right, these are atmospheric and environmental conditions that you have to take into account. Versus Colombia being closer to the equator, it's much warmer. Guess what? You have much higher productivity from the algae eating away those CO2. So a lot of the efficiency has to do with, where you're physically located and the limitations that you might have from the sun. But again, you're looking at the strains of the algae in order to adapt them locally for the best efficiency. And this is the pilot plant over in Argos, which consists only of 6 panels approached. And this is how it looks. These are a set of 3 panels that we have at the University of Miami, where we're looking at how do we implement and deploy the technology. Now that we have the algae, we know it works. How do you actually make it happen? How do you scale it to a plant? How do you build 12,000 of these? How do you connect them in a series of lines? How do you resolve a lot of the practical aspects? And I should give credit to one of my colleagues, Leonardo, who's in the room, who does a lot of the work, and I just do the talking. But so we are trying to solve those practical aspects that are the true limitations of the technology today. So the key aspects, we're looking at 86% efficiency of CO2, right? This is normal. This is not made up. This is a very high number, by the way. When I started in business, I thought it was Guinness, but it can happen. Again, in Miami especially, given environmental conditions. The nitrate oxides and sulfate oxides as well can be captured and removed. It is adaptable to all terrain, right? So if you're in a mountainous area, right, it's a matter of setting up these panels in arrays in order to adapt and design for the local conditions. And it is modular. We've been able, with the current design, to fit 13,144 of these individual panels in a 1 hectare. Ultimately, a cement plant is concerned about this. This is the space that I have. How can I arrange them? And how can I do? And what does that translate into the panels? So depending on the environmental area, you're looking between 2 and 5 metric tons of CO2 capture. Right? It's not a lot. 5 metric tons is not a lot, but okay, you're multiplying it by 12,000 panels. That's 60,000 metric tons annually that you could be capturing from a plant. That is significant. So it is a numbers game. And I'm not talking about carbon tax credits. I think that was discussed earlier as well. There is a financial incentive where it will become financially viable to invest in a farm like this next to a cement plant in order to make it happen. And that's only the capture, right? we're storing it in the algae. But guess what? The algae, just like the magnesium byproduct of the presentation earlier, also has a potential value, depending where you are, from bio fertilizer to food product to biodiesel, even though I would be very cautious of anybody that says that, because you really need to have a reliability that today is not there, right? But I think in the long term, in the next 10 years, we will see that as the volume and the capacity of algae expands, the productivity of biomass expands, and then you have a reliable source of biomass. But today, I think biodiesel and, cautious. I would be cautiously optimistic. But then you have additional value being there. And another item, very, very important with all these technologies, is data. Right? Hopefully, it's not just the numbers that I present, but you have to have traceability. You have to be able to measure the output of what you have. You have to be able to not only trace it and measure it, but also validate it, right? So in this system, a lot of the emissions and the outputs, together with Siemens, we've developed different sensors in a dashboard product in order to capture them real time. So the capacity is there, and the understanding of this data is also possible. So I go back where we started, which is, carbon capture and utilization storage represents over a third of the potential that we have to reduce and get to net zero. Those technologies are there, but they don't exist. They're not being implemented. These are very prototype, just like you saw. 5, 6 panels, 30 panels, compared to 12,000 panels for this technology. Very similar with direct air capture. Right? These solutions are at its infancy. But we're looking at 6, 7 years to really make it happen, to then have the next 25 years really to be able to deploy the technologies and capture all the CO2s. So it is very critical that we need to move fast and we need to invest fast. And I think a lot of it is through policy that is happening. So that being said, hopefully there's some time for questions. I'll be more happy to entertain them. Thank you.